So this is the 5.3 lecture on diagonalization. And here's our 5.3 handout. Recall that a diagonal matrix is a matrix whose only non-zero entries lie on the diagonal. We say that a square matrix is diagonalizable if it is similar to a diagonal matrix. Now, just before we go any further, let's just recall that two square n by n matrices A and B are similar if there exists an invertible matrix P such that A equals PB P inverse. And so a diagonalizable matrix is one where there's a diagonal matrix D such that the given matrix A is equal to PD P inverse. And so the question might be, well, why would we care about whether a matrix is diagonalizable or not? Why would we care about whether a given matrix is similar to a diagonal matrix? So I just want to give you a quick example of why we might care. And it has to do with making calculations significantly less complicated. So suppose we need to calculate a to the 50th power. If a is diagonalizable, then a to the 50th power is PDP inverse to the 50th power, which looks like a big mess. But if we write out PDP inverse, imagine that 50 times, right? Because of the nature of the product PDP inverse, each time we multiply by that trio again, the P inverse and P are up against each other, and they're going to cancel out in this product of PDP inverse to the 50th power. And each time they're up against each other, they cancel out all the way down the line. So we're left with just P times D times D times D all the way to the last D before the final P inverse. So PDP inverse to the 50th power will simplify to PD to the 50th P inverse. If we want to calculate a to the 50th power, we only have to calculate PD to the 50th P inverse. And this product involves significantly fewer calculations than calculating a to the 50th directly. Calculating the 50th power of a square matrix can be an enormously complicated computing task. But a diagonal matrix raised to the 50th power, it's just going to be the 50th power of each entry on the diagonal. So the computing is not so significant. So that's really what diagonalization is all about. Coming up with an alternative, simpler way to calculate quantities or products of matrices, because we get to exploit the fact that the things like the powers of the diagonal matrix are way easier to calculate. Let's get back to the handout now. And so we're going to move on to our theorem here. Let A be an n by n matrix. A is diagonalizable if and only if A has n linearly independent eigenvectors. So this is one of our most important applications of the idea of eigenvector. And this totally characterizes what it means for a square matrix to be diagonalizable. To determine that, we would have to find n linearly independent eigenvectors. In such a case, the n eigenvectors form what we will call an eigenvector basis for our n. There are n of them. They're linearly independent. The dimension of our n is n, so we know those vectors would have to be a basis for our n. Now, a little corollary here. If A is an n by n matrix and A has n distinct eigenvalues, then A is diagonalizable, because we already know if n has distinct eigenvalues, eigenvectors corresponding to those distinct eigenvalues will be linearly independent. What will be more challenging is when we do not have n distinct eigenvalues, how can we figure out whether a matrix is diagonalizable or not? And that's what we'll be looking at in the problems. Now, most of this rest of this page and the next page on the handout has to do with the proof of the main theorem. I'm not going to go through those details here. I'll let you read that over. And actually, the proof is actually very similar to the calculation we're going to go through. So I think if you understand the calculation, I think you're going to have a good understanding of the gist of the proof of the main theorem for this section. So we're going to move right into this problem on page 3, where we're going to actually diagonalize a matrix A. And this is one of the kind of main results of our course. This is a big kind of test problem kind of thing, or final exam kind of problem, to be able to diagonalize a square matrix. So here we go into the process. To diagonalize A, what we're going to have to do is find an invertible 3 by 3 matrix P and a diagonal 3 by 3 matrix D such that A equals PDP inverse. And our solution is outlined here right on the handout. This is the process we're going to go through. We're really finding the eigenvalues and finding linearly independent eigenvectors is going to be the key to describing both the diagonal matrix D and the matrix P. So let's go ahead and just plunge into these steps here. So the first step is to find the eigenvalues of A. So we need to look at A minus lambda I, which is going to be the matrix minus lambda 0, negative 2, 1, 2 minus lambda 1, 1, 0, 3 minus lambda. And we need to actually calculate the determinant of that matrix A minus lambda I. And so we gotta pick a row or column to expand along, and maybe I'll just go ahead and pick the first row to expand along, plus, minus, plus. So this is a calculation we've gone through several times, and here we go again. I'm going to have minus lambda times plus 1 times the determinant of the 2 by 2 matrix with these entries, and then plus 0, and then plus a negative 2 times positive 1 times another 2 by 2 determinant with entries 1, 2 minus lambda 1, 0. So I have minus lambda times 2 minus lambda, 3 minus lambda, minus 0, plus a negative 2 times 0. I think it's going to be minus 2 minus lambda. So minus 2 plus lambda. And I have to multiply all this out, and I'm just going to tell you what I get here. Let's see, there's no trickiness to this, so there's a clever way to multiply this out in factor. If we multiply it out all the way, it becomes minus lambda cubed plus 5 lambda squared minus 8 lambda plus 4. And there are ways to look for roots and factors of this. I don't want you guys to worry about this. I'm not going to give you anything this complicated on a test. I could also factor out a 2 minus lambda from the algebra of this. If I factor out a 2 minus lambda, I'm going to have 2 minus lambda times minus lambda times 3 minus lambda. If I factor out 2 minus lambda from here, it's like I'll have a plus 2 on the end. So I have 2 minus lambda times minus 3 lambda plus lambda squared plus 2. And there's a quadratic that I believe I can factor. I get lambda minus 2, lambda minus 1. Now 2 minus lambda, it's just a negative lambda minus 2. And so what we see is that this is minus lambda minus 2 squared, lambda minus 1. So again, don't worry about the fancy algebra here, because I won't give you one that's so difficult to factor the characteristic polynomial. But what we see here in this example is that the eigenvalues are lambda equals 2 and lambda equals 1. Lambda equals 2 has multiplicity 2 because that factor occurs squared. So that's actually the end of step 1. So we found our eigenvalues. Now what we're going to do is check for a basis, look for a basis for each one of the eigenspaces. So in step 2, we're going to look for a basis for, let's take the lambda equals 1 eigenvalue. So I have to actually look at A minus 1i. So I'm going to plug in 1 in the place of lambda, and I get negative 1, 0, negative 2, 1, 1, 1, 1, 0, 3 minus 1 is 2. And we got to solve A minus 1ix equals 0, the homogeneous equation. And so I have negative 1, 0, negative 2, 1, 1, 1, 1, 0, 2. Of course, my augmented matrix here will have this extra column of zeros, which won't really change much as I go through row operations, right? Here, if I row reduce, I'll just say row ops. Here's what I get. I get a column 1, 0, 0, 0, 1, 0, 2, negative 1, 0, 0, 0, 0. So that's in reduced form. I can see that I have pivots for x1 and x2. x3 is free, so x1 plus 2x3 is 0. x2 minus x3 is 0, and x3 is free. And so my general solution is going to have the form minus 2x3, that's x1, x2 is x3, x3 is free. Looks like it has the form x3 times negative 2, 1, 1. So it looks like we have a one-dimensional eigenspace, and there's our basis vector, right? In fact, that's negative 2, 1, 1 is an eigenvector corresponding to the eigenvalue lambda equals 1, and negative 2, 1, 1 is actually a basis for the eigenspace. There's times here. So this is the vector we're going to pluck off in a little bit. We got to remember that we got that. That's our basis vector for the lambda equals 1 eigenspace. Now let's do the same with a basis for the lambda equals 2 eigenspace. And so, of course, we got to look at a minus 2I, which is going to be negative 2, 0, negative 2, 1, 0, 1, 1, 0, 1, I believe. Okay. And again, we got to solve a minus 2I x equals 0, the homogeneous equation. So take our augmented matrix, column of zeros, and apply row operations to row reduce that. And it doesn't take long to do that. I got 1, 0, 1, 0, and 2 rows of zeros. So I have just one pivot position. So x1 plus x3 is equal to 0. And x2 and x3 are both free variables for that matrix equation. And so my general solution here is going to be x1 is minus x3, x2 is free, x3 is free. So I can write this as x2 times 0, 1, 0 plus x3 times negative 1, 0, 1. And so a basis for the lambda equals 2 eigenspace is going to be a set of these two vectors, 0, 1, 0, and negative 1, 0, 1. So I have a two-dimensional eigenspace here corresponding to the lambda equals 2. And well, okay, so we got our basis for the lambda equals 1, basis for the lambda equals 2 eigenspace. And I've got another piece of paper here. I think I'm going to try to just sum this up. So the lambda equals 1 basis consisted of just one vector, negative 2, 1, 1, and the lambda equals 2 basis consists of two vectors. We had 0, 1, 0, and negative 1, 0, 1. So now step 3 of the process is to construct the matrix P. The matrix that will work for P is constructed from the eigenvectors we got in step 1. I can put these basis vectors in any order, but I just need to be consistent when I construct the diagonal matrix D, as we'll see in a second. So P, I'm just going to take this first vector, negative 2, 1, 1. Then I'm going to take 0, 1, 0, negative 1, 0, 1. As long as I have enough basis vectors, here I would need 3 for a 3 by 3 matrix, I'm going to have an invertible matrix here. Those 3 vectors are linearly independent. We know the basis vectors for distinct eigenvalues are independent of each other, and then we know these 2 guys are independent because they're basis vectors for the lambda equals 2 space. And if the columns were not linearly independent, if these 3 vectors weren't, we'd be in trouble because we wouldn't be able to find a basis vector. So that's our step 3, and really we're just writing it down, the matrix P. I wasn't using those basis vectors, the basis vectors for the eigenspaces. And now step 4 in the process is to construct D. The diagonal matrix, and the diagonal matrix is going to have eigenvalues on its diagonal entries. You have to make sure the eigenvalues used in D match the corresponding columns for P. So the first column of P came from our lambda equals 1, so I need a 1 appearing on the diagonal in the first column, so 1, 0, 0. Then the next 2 P columns came from the basis for lambda equals 2, so I need to put a 2 again on the diagonal, and I get another 2. That kind of is a reflection of the fact that we had multiplicity 2 here for that lambda equals 2 eigenvalue. And again, P has to be invertible. You don't have to actually calculate P inverse. We got our P, we got our D. We can check by calculating now AP and PD, because AP should equal PD, because AP P inverse will equal A, and A would be equal to PD P inverse. That's really our similarity relationship between A and D. But all we got to do is check that AP equals PD, and it's a check just to verify that we haven't made a mistake. AP is where's my A matrix? Oh, I got it here in front of me. 0, 1, 1, 0, 2, 0, negative 2, 1, 3, and P is negative 2, 1, 1, 0, 1, 0, negative 1, 0, 1. Okay. And you can check it out. I get negative 2, 0, negative 2, 1, 2, 0, 1, 0, 2 is AP. If I check PD, so I'm recopying P again. Times my diagonal matrix D. The eigenvalues on the diagonal. And PD, again, I can go through the whole process to check multiplication. And here, these are equal, the same. And so that just confirms the similarity relationship between A and D using, this sort of equivalent form of it. And we're done. Again, our goal was to diagonalize the original matrix A, and that really was accomplished once we found the two matrices P and D. And the way that the eigenvector basis vectors relate to the eigenvalues as on the diagonal of the D matrix really kind of reveals how that theorem is proved, where I didn't go into the theorem details. So I'm going to stop with at this point on this exercise here, and we're going to continue in another separate video the rest of this section.